morning, everyone. It gives me enormous honor to introduce Professor Glaucio, the recipient of this year's Eringen medals. Professor Paulino is currently the Margaret Augustin Professor of Engineering at Princeton University. He has made many, I will call him a world leader in this area called topology optimization. If you ask what is the most critical development of design technology in the past 20, 30 years, many people will tell you it is topology optimization. On the other hand, many of us consider topology optimization as a ill-defined or posed problem because there are many practical challenges of really implementing the method to make it useful. So throughout the years, Glaucio has made many fundamental contributions for solving what we call the most difficult problems in this field. And I think the most critical contribution is really he brings the rigor of mechanics into topology optimization. And these difficult problems including considering fracture, large deformation, considering large-scale, multi-scale physics, multi-physics problems. And he really made this effort. I would think that throughout the years we have seen many excellent papers published that try to really make topology optimization accessible to scalable design as well as now we call the deployable structures and the metamaterials. We have seen many of those papers in this conference. There's many awards that he received that I can tell you, but I will just highlight just a few. First, he is a fellow of many society. In recent years, he received the Daniel Drucker Medal of SME, as well as the Raymond Mading Medal of the ASCE, so he's actually active in both mechanical as well as civil engineering. And then the Reddy Medal from the Mechanics of Advanced Materials and Structures. He was elected to be the member of National Academy of Engineering. And I also like to mention that he has really played a great leadership role in the community. Some of us will still remember that he was the president of this society back to 2018. He also served on the board of the EMI. About a decade ago, he took the critical responsibility as the National Science Foundation, served as the director of the mechanics program. I want to mention that he is the person that really pioneered the Odyssey program, which really sparks the origami engineering, research, and development in US and around the world. And throughout the years, he has made a great effort to bring multiple communities together, materials, mechanics. Now we see this here in this conference, many people from manufacturing, and myself is coming from design. So this community, the growth of this community, we like to tribute to leaders like Professor Paulino. Without further ado, let's welcome Professor Paulino.
Good morning, everyone, and thank you very much, Wei, for such a wonderful introduction. And actually, you introduced me as a researcher, but also as a person, and also provided an extra introduction to my talk, because I was thinking if I should include some slides about the Odyssey program. I did not, but you talked about it. Thank you very much for providing the introduction of the lecture. I am going to talk about origami today, and since the title is too short, maybe it will be on origami engineering, or maybe engineering origami, or if you want more details, maybe origami engineered metamaterials, structures, and something else that may be dictated by your imagination, and it may happen that the most interesting things from this talk may be things that I did not tell you than the ones that I will tell you. Before I move on, I would like to acknowledge some wonderful collaborators that I had through the years. Dr. Tuozal here. Thank you, Tu. You have been such a great collaborator. Evgeny Filipov, I think he's also here. Tomohiro Tashi, my friend Horacio Espinosa, he might be here. Sirida Krishnasamy, Diego Miseroni, Kelly, Chris, Pradeep Pratapa, Larissa Novellino, Heimin Wei, Nicholas Alderet, and Zhao Wenling. And also I would like to thank the sponsors of this work, especially the National Science Foundation, JSPS, CST, and the Margareta Augustine Professorship at Princeton. Recently, one day I received this magazine in the mail from a great friend, Jason Patrick. Is he here? Thanks, Jason, for sending the magazine to me. National Geographic published a special issue in February in origami, because origami is quite pervasive. Origami has impact and influence from education, engineering, science, technology, art, space. It's impossible to go to space without origami. Anything that you put in a rocket has to be very lightweight, very effective, very functional, but can only be deployed when you reach the destination, and the origami plays a major role there. And as they say that the future is folded, how origami is reshaping our world, I recommend that you take a look in this special issue as a very modern presentation of the topic. Origami, to relate to the talk yesterday by Julio Otino, right? He tried to combine engineering and art. Origami has its roots on art, and here is a great piece of work by Satoshi Kamiya in Japan. That's the dragon model. You can see that the level of detail here, the scales of the dragon, the crease pattern is asymmetrical, yet it produces a symmetric model. Look at the level of detail, the head, the horns, the feet, the claws, and this is one piece of paper, folding only, very restrictive. One piece of paper, folding only, very simple. This piece of work is in the Origami Gallery in Japan. Here is my favorite piece of origami. I always like to share that because Eric Joissel is one of the origami masters that I admire the most. He's quite amazing. This is the orchestra. If you count, there are 11 musicians and 11 instruments. 22 pieces of paper. One piece of paper for each musician, one piece of paper for each instrument. If you look at the finesse, at the expression, this is just 22 pieces of paper. That's it. But look at the expression, look at the art, look at what it communicates, the creativity in this piece of work, the innovation, even in the field of origami and beyond, is quite amazing. And this piece of work, or part of it, is in the Origami Gallery in Japan. If any of you go to Japan, to Tokyo, stop by the Origami Gallery. It will pay off, trust me. And this leads to our origami-inspired metamaterials. And first I will talk about some Lego metamaterials, a work that I did in collaboration with Dr. Tuozal on metamaterials that are modular, reconfigurable, and multi-stable. And I have a disclaimer here, this is unpublished work. We wanted to tell you something new, interesting, not published yet, and that's the idea here. So, most of the origami is based, let's say, paper, surfaces, shells, right? And here is what, on the left, is what is called the Kreslin pattern. Each unit is a unit of the Kreslin pattern, and it's a shell-based, right? And this origami is very interesting because it couples 2 degrees of freedom, the axial and the twist, and leads to 2 stable states. And what we did recently was a rod-based version of the shell, okay? So that hopefully what you see here on the right is equivalent to the left. And we have 2 stable states, as I am showing here, the deployed and the folded. And these states are characterized by these angles here, Phi0 and Phi1 of the faces. And then I can go and write an energy function for this. For example, a quadratic energy function where I can capture the energy from the mountain creases and the valley creases here in green. And this B bar, C bar, these are the reference states. Okay. And then when I plot this energy versus this twist angle, then we can see that these stable configurations are here, and the energy here is 0. Pay attention that at this minimum point here, the energy is 0, and that's what we have. But when I talk about frustrated states later in the talk, halfway in the talk, then we are going to have frustration and pre-stressing in the system, and this energy level that correspond to the minimum points will not be 0. And we can do calculations and find what these angles are, as we have shown here. And then we can program the instability playing with geometry and material. Sometimes we don't know what is the difference between geometry and material. And then we can see here that we can play with the Kreslin in terms of polygons that have 4 edges, as you can see, 5, 6, and so on. And to make this like Legos so that you can play with it, then we just put small magnets here so that they can easily connect to each other. And when I put them together, then they have to satisfy this compatibility condition so that each piece can be put together. And if we look, for example, at the energy versus the twist angle, we can see that the lower the number of edges, the higher the energy barrier. And if I keep the geometry, then and I use stiffer materials, then I have a higher energy barrier. And when I put them together, I will always make sure that when they are joined, that I have opposite chiralities, as you can see here. We designed this using a gradient-based min-max topology optimization, and the objective is shown here is the minimization of this quadratic function between where we minimize the difference between the desired state and the calculated state. The design variables here are the cross-sectional areas that we are going to design, and we have a volume constraint and some nonlinear state equations that will govern the behavior. In general, most topology optimization work, and Professor Wei Chen has contributed a lot in the field, is based on density-based methods. But here, we did this, since we are using a rod-based method, we did this using a ground structure method. Essentially, we have a design domain, we have many points, and then we connect each point with every other point and have a truss member there. Then the optimizer will remove, most of them are not needed, almost all of them are not needed. The optimizer will remove almost 100% of them, 90+% of them, and at the end, if things work, I will get a configuration like this that will work. And essentially, this min-max configuration is done by means of some prescribed data, prescribed behavior that I want. I want to program the material to behave that way with these points, and then the optimizer is going to give me a potential result that will have this nonlinear behavior that I'm looking for. And then I can play with geometry and material. For example, here I'll keep the material the same, just change the geometry. The first two here have 8 sides, then 6, then 4. And then just remember, the lower the number of edges, the higher the energy barrier. Therefore, the middle is going to buckle first, as you can see here. And then the next two, that are the 6 bonds. And finally, the 4 cones. So here, the material is the same. We just played with the geometry. And then now I can keep the geometry the same, for example, and use different materials. And then I can define, I can design different low displacement landscapes and different multi-stability configurations, as you can see here. But everything here is 1D. If we are claiming there is metamaterials in the title, then the materials have to have a three-dimensional feature, and then we can assemble this, for example, in 3D, as you can see here, and we would get some multi-stable behavior, as you can see on the right. And here, what happened is we have three colors, three different materials. The blue is the less stiff one, and then the next one is the white, and the yellow. Doesn't matter where I put them. Doesn't matter. You are going to see that first the blue will be activated, and the others wait, and then after the blue finishes its job, then we go to the next one. And then you can change this as you wish. You know. Actually, when children comes to our lab and play with this, they love it because it's very nice to play with this. Origami is good for everybody, not just us. Children, adults, and also it's very good for me because when I retire, then I will have something to do. As I said, you can play with this and give this to children, and then we have lots of Legos here, and then we just distribute them as you show here. And then how do you play with this? Let's see the first one. Then you can see that we get more or less an ascending peak loads, right? It is multi-stable behavior. The next one, for example, I may want all the peak loads to be the same. This one, a small one and two big ones, or the opposite, and so on. And this is a work in progress, unpublished, but I decided to share this with you. And then now let's continue on the origami-inspired metamaterials. And I have talked to you about this rod-based origami. Now I'll talk about origami that is based on shells, and I would like to concentrate in this work that I did in collaboration with Professor Horacio Espinosa and collaborators. And we wanted to go in lower scales with the origami and see how it behaves. And then we decided to study the micro-scale origami architected metamaterials exhibiting macro-scale reversible auxeticity. We can see here that, for example, we can have some Murray strips, and I put two Murray strips together, I form a tube, and then I can go and assemble these tubes as we are showing here. If I can align them in this direction and have them in a special configuration that is called a zipper type configuration, and have this metamaterial that we have shown before has very special properties. But we have investigated this at the macro scale, and then the key idea was to try to do this at the micro scale. You can see here the whole thing is about 30 microns. Then the metamaterial may be around, 100 microns or so. And you can see that the features are quite small. The platelets are about 13 microns, and the thickness is about 1 micron or so. And at the time that we published this, this was probably the smallest origami metamaterial that had been done. And one contrast I would like to make is that most metamaterials, many times they are lattice-based, but this one is based on shells, right? Everything here is made by this shell arrangement. And Horacio gave a talk and talked in very detail about this work in the Eringen symposium. I'll just highlight a few things. You can see here that if you do in situ SEM testing and look at the stress strain behavior, and you just test in this direction, for example, the X direction, then you can see here very interesting behavior. This is the loading scenario. We have a modulation phase. These are polymer type materials. We need to modulate the material, and then we load and we keep doing that. And you can see the modulation phases here, and there is always some change of stiffness between each modulation step. And you can see that, for example, here we have a very interesting behavior, right? We have this hardening here, and then we have some sort of a plateau, and then we unload. And the interesting thing here, if you look, this is the configuration 1. If you look at configuration 5, is where the load is applied. You can see it has deformed a lot. It's tremendously deformed. And, but if we wait a little bit, the material almost recovers completely. And that has some very interesting hysteresis behavior. If we just do the same in situ SEM test, but just change the orientation, just test it in the y direction, now you can see that we have just a hardening behavior. But again, when I unload the same behavior, you can see it start here at 1. If you look at 5, this has deformed a lot, but when we unload, wait a little bit, then the material almost recovers completely. That's very nice. And all the details of this work are in this paper that we publish in small, and I refer you to the paper, and I'll be glad to talk more to you about this work. So, so far I have talked about rod-based origami, shell-based, rod-based, the cylindrical type that can be assembled in 3D, and talked about metamaterials, right, that are a combination of tubes and assembly of tubes. Now, and for the remainder of the talk, I would like to talk about tessellations. And you may agree that there is a professor, I always ask Professor Ringen, Ringen, are you here? Over there. You may agree that the most famous developable pattern is the Miura, right? And the most famous non-developable is the egg box. And most patterns have some feature of both, right? So and these two have some very peculiar behavior. For example, here is the Miura ori, and in plane, it has a negative Poisson ratio. You shrink in one direction, you shrink in all the directions. Out of plane, it forms a saddle type configuration, as you can see, and the egg box is the opposite. In plane, it has a positive Poisson ratio, like most materials, but out of plane, it has a negative Poisson ratio, and forms this dome shape that is typical of auxetic materials. As you can see, these tessellations are very beautiful. They have a lot of features, symmetries, anti-symmetries, and a lot of behavior that is associated to their geometry, the periodicity. And several groups have studied these tessellations, and they have noticed a tremendous elegance in the geometric mechanics of the origami. For example, the group at Harvard, the Mahadevan's group, some time ago, they studied the Miura pattern. They parameterized it, as you see here. And after a lot of math and derivations, they computed the Poisson ratio in bending, and then the Poisson ratio in stretch. If you just take a look here, they are identical, except for the sign. One is the opposite of the other. Later, a group in France studied the egg box, and then they derived, after a lot of math, it's a very long paper, then they were able to derive analytical expressions based on the parametrization of the egg box for the Poisson ratio in bending and the stretch. And take a look. Very elegant, very interesting. They are identical except for the sign. And later we also studied some of these patterns, but one thing that you see is that, as you can see here, Miura is Miura, egg box is egg box, right? These are two different materials. Wouldn't it be nice if we could have both, since they are so opposite of the spectrum, and as Professor Ringen agreed, most materials would have behavior that is a combination of both. Wouldn't it be nice if we could have these two material configurations in the same material system? And if I am asking the question here, it's because the answer is yes, and that's what we did. With the morph pattern, for example, here's the same material. I embedded all the, encoded all the unit cells with the Miura mode, and then you can see it has exactly the same behavior as the actual Miura. And then here I change. Here's the same tessellation, just change the encoding to be egg box, and then you can see it has the expected behavior. And here is our new metamaterial with the just changing the encoding, the same material system, and you can see that the behavior is exactly what we anticipated, and now we have this metamaterial with the possibility to encode both modes, either a Miura or an eggbox mode. How do we do that? I will explain in a second. And then we also did a lot of work to understand how this behave, and especially about the Poisson ratio. And as you define the Poisson ratio, for example, in stretch as the negative of the stretch ratios, in bending we do the same. We define the Poisson ratio in bending as the negative of the curvatures in the two directions, as I am showing here. And then after you do all the derivations, we got this Poisson ratio in bending, as you can see here, given by this expression. And you can see the expression is beautiful, you know. Even if you don't know what the result is, because the tessellation is so beautiful, the result has to be beautiful. And you can see that there is some symmetry in the expressions here in these results, especially, for example, the terms in parentheses and so on. And then we did the derivation in stretch, and take a look. They are very elegant, very beautiful. And the only difference between the two is the sign. And then we have this beautiful property. And we also can show that the previous derivations for the eggbox and the Miuras, they become particular cases of our general expression. All these ideas are summarized in this paper we wrote in PRL on the geometric mechanics of origami patterns exhibiting Poisson's ratio switch by breaking mountain and valley assignment. And we started here a mathematical framework to describe the origami that recently we were able to generalize in this paper that is in PNAS, was published last year, that shows that discrete symmetries, they control geometric mechanics in parallelogram-based origami. And what I find interesting here in this work is that we use a theory that uses the features of the origami itself. For example, if you use a general method to analyze origami like finite elements, it has no idea that what you are analyzing is an origami. But here, for example, the mathematical framework is composed of vertex operators, edge operators, panel operators that are intrinsic to that geometry that will allow us to understand the geometric mechanics of the pattern. And now, let's take a look at the morph pattern, and let's look at its design space. What happened is, let's say I have these angles here, alpha and beta, around the vertex, and we can see that here, alpha and beta for yellow is the morph pattern, and when alpha equal beta, as we can see here, then I am going to have the egg box behavior. And for the Miura, when beta is pi minus alpha, that is shown here, I have this blue behavior. But the morph then can have a much richer design space. And this is achieved by controlling this crisp pattern here, that I will elaborate a little bit more as I show you here that we can go from a flat folded state to the egg box mode, to a transition mode, to a Miura mode, to another flat folded state. And then, when we compare here the behavior, for example, we can see here, this is well known, this is from work of previous colleagues, that egg box, when I look at the egg box versus the phi angle, in general, I am going to look at these angles here, psi and phi is this angle here that is parallel to this crease here that will change the mountain valley assignment. Then we know that the Poisson ratio is positive. This is not our work, this is from the literature. And here, for the Miura, we know that the Poisson ratio is negative, and again, this is not our work, this is the literature. But then the morph, something very interesting that we see is that it can change this Poisson ratio from negative to 0 to positive. And that's what the theory there was. Is this true? The only way to see that is by means of experiments, and then we are going to verify that later on. Now, let's look at the configurational space of the morph, where I use this terminology here. The gammas are the dihedral angles, and you look at the C and the phi angles, and the panel angles are alpha and beta, as you can see here. And the angle that is shown here is the same angle for each parallelogram close to the vertex. This is alpha, this is beta, this is beta, this is alpha. And then I can derive the configuration of space, and then I can do some derivatives here and use some spherical trigonometry, and we can show in this psi-phi configuration of space that the corresponding configuration here at the peak, that is this gray line that you see in the psi-phi curve, is the transition state that corresponds to gamma 3 equals 0, is when we can flip from mountain to valley and vice versa, and that will change the properties of the material tremendously, right? And then you can see that when this term here is 0, then this will be 0, right? Because this term here will be 0. And here I'm plotting several configurations where to the right, the pattern will be in the egg box mode, to the left in the Miura mode, and I chose here alpha plus beta to be 100 degrees, and this is the configurations that we get. What do we do with this? For example, we can have a kinematic bifurcation, as I'm illustrating here. This is a 3 by 3 cell, and then all of them are in the egg box mode. They will reach here, and then they are going to change to the Miura mode. And now, when I go back, what I am going to do is to have the unit cells at 10 points transition from the Miura to the egg box, forming a hybrid pattern, so that here then I would have a combination. And then I can use this any way that I wish. For example, I can go and encode half of the tessellation with a Miura, half with the egg box when it bends. This here bends more or less like an egg box, this bends more or less like a Miura, but this is the morph pattern, or I can alternate the encoding or do the encoding any other way that I wish. Now, does that theory make sense? Is that true? Then we did some experiments with a 1 millimeter thick polypropylene sheet that was milled with the CNC machine. You can see here the size of the tessellation, and here you can see the units of the pattern, and this has to be done with extreme care. Origami is wonderful, it's great, but it's very unforgiving. Anyone that works here in origami, I think, would agree with me. It's very unforgiving. If you do things very precisely, the key word is precision. Things in general works very well, but if you sacrifice the precision, then you pay the price. And then you can see here that we have some manufacturing parameters that are explained in the paper, in addition to the theoretical ones, because now this will have some thickness, and we have to do this with some extensions and seats, and remove the right amount of material that will provide the hinge location so that this can behave in the way that it should. However, when we do testing, what happens is we can only do a finite size, and then when we pull on this, we have always this dog bone shape, and that is no uniform transverse deformation that pollute the results. And the question is, we want to have a uniform transverse deformation and no dog bone shape. And this is what we did in this paper that was published last year in Extreme Mechanics Letters with a novel setup for origami experiments. And the key idea is to design the fixtures. I will not show you the design now, but I'll show you the design in a few minutes. But for the time being, just believe that if you have these Saint-Bernard fixtures that allows you to test the periodic pattern, then you can get excellent results. And if you use standard fixtures, then when you do the experiment, things may jump and the results may not be as clean. So let's see how this behaves. So here I am going to start with this tessellation here, and the notation I'm going to use that the number of Miura cells is 0. So because everyone is in the egg box mode, okay? And then here's the envelope C, and here is the test. Here is the observation region. It's like a digital image correlation type so that we can compute the Poisson ratio. And take a look here. I have 3 results. First is the theory, is the equation we derived. Okay, is the Poisson ratio versus the envelope C. Next, we did numerical calculations using the Merlin software. Merlin is a software that we developed some time ago to provide a fundamental framework to understand the nonlinear mechanics of a non-rigid origami. And that's what we used here, and the blue are the experiments. And these results use the new fixtures. The old fixtures would not provide this level of agreement. And the next, what I am going to do is to encode just one layer of Miura cells. And now, as you know, the Miura has a negative Poisson ratio, then it tends to bring the results here to the right, as you can see here. Okay? But this is the same tessellation, the same pattern that is being tested. Okay? And now I am going to have 2 Miura unit cells. And something very interesting is going to happen now. Take a look, these are 2, and there is only 1 row with the egg box. Now, what you can see is that it has a nearly 0 Poisson ratio for almost a huge range of this envelope C, this folding envelope. And then later it will become negative. And finally, we switch and have everyone in the Miura mode and in the, as you can see here. And then in the interest of time, I'll just show you here the final result that all the results are quite, they agree quite well, the experiment, the simulation, and the theory, and you change from positive to 0 to negative, the same tessellation. All right, and here are some of the low displacement results. And now the key idea is here we have an homogeneous sample on the left, and then with the morph, for example, we can create a line defect type, but the question is, can we have defect in multiple directions, like line and the point defect? With the morph, we can only achieve this level, and the answer is yes, and this is summarized in this paper that we published in Advanced Materials. And here is the idea of the pattern. Again, going back to the Miura, as you can see here, has a lattice in the orthogonal space. This angle is 90 degrees, angles alpha and pi minus alpha. Here is the egg box. All the angles are alpha. Again, orthogonal lattice. But the trimorph is the new pattern we developed, is not in an orthogonal lattice. And this is the key to get the features that we are looking for. And the angles are alpha, see? And here is alpha plus delta, alpha minus delta. And let's see how this works. Here is the schematic of the pattern. Annotation is very similar to before, but now because the pattern is more involved, then I color-coded here the 4 panels, okay? And then we have, as you can see, these 2 angles here are alpha of the blue, and the green, this is alpha plus delta, alpha minus delta, and these angles are the same at the vertex of the pattern. And then I have here my configuration space, and I can derive this. That is given again by this very beautiful expression. And the coefficients here, D, E, and so on, they are given in terms of these psi and phi angles, and alpha and delta angles. And just remember that this is in the triclinic space, so these angles that are not necessarily 90 degrees, and here is the pattern in a Cartesian frame. Now let's quickly look at the configuration space of the trimorph cell. And again, looking at this psi versus phi angles. And now I have 7 configurations here. And the color coding is very helpful. And you can see something very interesting. I start here in configuration 1, and this is in a certain type of mirror that we call mirror type 1, and there will be a transition phase here, 3, that will transition to an egg box, and again, there will be another transition here, 5, that will transition for another type of mirror. Also notice that there's a beautiful configuration space, but notice here that 1 and 7 seems to be at the same location, but there is a discontinuity. They could not be more different, right? It's like when you get a piece of paper, if you fold it in one way, and in the other way it look exactly the same, but are totally different. Take a look here. If I look at this configuration space, and then I vary the angle alpha, right? That is this angle here, the panel angle. Because this angle I choose, right? This angle I have to choose the length of the edges and the angle. When I choose that, I get the pattern. And then, as you can see here, when alpha becomes 90 degrees, then the egg box mode disappears. There is no green color here. And this becomes the Barreto-Mars pattern. So it's very rich. We get another type of behavior, and this Barreto-Mars, for example, is a very interesting pattern, for example, to control friction in surfaces, for example. And then, when I look here, and I vary the angle delta, and again, this angle here is, again, the panel angle, and I can choose that. Then you can see that we start with a pure egg box mode. There is no yellow, no green here when at this endpoint. And then when I keep changing this angle delta, then the other two mirror type modes, they appear. Then it morphs from a pure egg box mode to another mode with two mirror modes and another egg box. And this here is an illustration of the 3 unit cells that will give me different behavior of the tessellation. Here are the spherical polygons, and we can do that using spherical trigonometry. And here are the Gauss maps. What is very interesting is that in general, the Gauss map of a mirror is a bow tie, but you can see that the two of them, they have a completely different orientations, and the Gauss map of the egg box is a spherical polygon. That's what we get here. And the interesting thing is that this allows us to connect the mathematics of spherical trigonometry with this programmable states of matter, so that it can allow us to program the material. Again, we did a similar math to what we have shown before, so that we could calculate analytically the lattice-Poisson ratio, and because we are in a triclinic space, we also look at the shear normal coupling, just this negative of the ratio of the shear to the normal strains that is given by this expression. And let's take a quick look at these experiments. And I'll try to speed up so that we can have some time for questions. And here I need to stop right here, because I didn't explain to you about the idea of the new fixtures that allow us to do experiments with very small samples and still representing the periodic system. Then this is composed of a slider system and railing systems, and here there is almost frictionless connections, so that whenever the tessellation tries to deform, there will be no resistance. And here is a locking system, because we don't want rigid body modes in the tessellation. And then we have this rail, the sliders, and the locking system, and this two-piece connector. And these pieces then are connected properly to the tessellation, as you can see here. And like before, this is our observation region. And I would like to show you the experiments here where we are going to get the Poisson ratio that will switch from positive to negative, as you can see here. And here is in a kind of egg box mode. Now it will become, you can see here the evolution of the experiment. Then it becomes 0, and then Poisson ratio switch, and it will become negative. And we can also see the shear normal coupling evolution here. And now, using the same tessellation, we are just going to do the opposite tension, where the Poisson ratio will change from negative to positive. And you can see here that the match between the experiments and the theory is pretty good and allow us to investigate this Poisson ratio switch. Okay? Now let's talk about the importance of using frustration. Well, sometimes frustration is not good, right? Especially in life. But sometimes frustration can be pretty good because it can allow us to design and reprogram materials. Changing the levels of frustration, we can change the material behavior. Well, what we decided to do here is, since we are, everything I have shown here recently is a 4-degree origami, 4 parallelogram, and then we decided to have 2 hinges that will have same folding stiffness, and 2 of them that will be nearly 0. And then I have here the kinematic path, gamma 1, gamma 2, and the energy contour. When these here coincide, we can look here at the energy versus the dihedral angle gamma 3 of the tessellation, and this is one of the angles that can switch. Then we can see the energy landscape here, and the theory is a quadratic energy function. And this gamma 1 bar, gamma 2 bar, this is the reference state, our neutral state. And you can see here I have these points 1, 2, and 3. One thing you'll notice is that 1 and 3 are symmetric along this line, and 2 is in the 45-degree angle where gamma 1 equal gamma 2 that will represent the egg box mode. Because this is a pre-stress system, there is a level of frustration. Notice that this is not like before. In the first few minutes, the energy for the minimum energy configuration was 0, but here it will be always finite. That will depend on the level of frustration in the tessellation. And here is the way this was done. And then this will illustrate what I have just shown you. And these here are the dihedral angles. These are the rigid panels. These are the elastic hinges that will impose the pre-stressing, and these are the free hinges. And here I have 3 stable states, and you can either hear them. Then I'm changing from the egg box to 1 Miura mode, and then from the egg box to another Miura mode in the frustrated system. The tessellation is frustrated, or the unit cell is frustrated, but all the assemblies will be frustrated, and this snapping behavior happens in the column behavior of the tessellation, as you can see here, the row behavior, as you can see here, and also in the assembly, in the actual tessellation, as you can see here, and you can hear it. And here is a summary of what I have shown, and then finally we could achieve these non-rigid modes, and then we did simulations to understand this. In the interest of time, I will skip those, and then we went here from the homogeneous state to a state with 1-line defect to 2-line defects, where we are going to have a point defect. Now, if this is the energy distribution, that you can see most of the energy is to fold the hinges as we expected, but there is some energy that will be spent to bend the panels, and very little energy to stretch the panels. Now, if you look at the gamma 1, gamma 2 space, you can see that, as I have shown before, this is the rigid origami type of behavior, and I start here with 1, that is this homogeneous state, and I go to 2. As you can see here, I can do this, and that's what I did with the morph, for example, really with rigid origami assumptions. However, when I start to create, for example, the point defects, then it becomes more and more non-rigid because of frustration that has been introduced in the system, and the system will have the defects, and the system becomes more and more non-rigid, as we can show here. Finally, this summarizes everything, and after that I can answer questions. glad to answer questions.
Thank you so much, Glaucio, for this beautiful talk that really leads us into the scientific world of origami. We have time for a few questions. Yes, I saw a lead. Yeah, you first. We have a microphone? Yes.
Yeah, Glaucio, as usual, beautiful, beautiful. Science and art and all merged, and mathematics. One question is, when you showed the defect, if you have multiple defects, do you expect some interactions between them?
Yes. Well, you always ask excellent questions. Yes, we have not, this is what we plan to do next. Yes, there will be interactions among them, and these interactions will provide us with different behavior. As new defects are nucleated, is a material that didn't exist before. It's a new material. And then we also plan to investigate, depending on their location and arrangement, that will be short-term interactions, short-range interactions, and long-range interactions. And we may even observe some very interesting features. For example, like what comes into my mind was a defect paper that was published by Itag Cohen group in Science some time ago, just introducing point defects in the Miura, and they were able to discover some new behavior and features. This is what we plan to do next. We have not done that yet.
I have a question. First of all, congratulations. Fantastic results, big contribution to mechanics. I have a question from the viewpoint of damage and fracture mechanics. So you have segments of decreasing energy, which always goes to instability. Like, for example, changing angle, going from egg box pattern to Miura. Now, if it's a larger system, I would expect would lead to some propagation of the morph. That would not happen simultaneously, and that would be of interest for structural safety and design.
Correct.
Have you studied that, or is it being studied? I'm outside of this.
No, it's a very good point. And the mechanical behavior of the pattern, let's say regarding fracture, for example, because if you use this in actual applications at some point, you may have failure, you may have damage, you may have fracture, and this needs to be investigated. But this is so difficult that we have not done that because we were trying to understand first the math and the mechanics, the geometric mechanics of these origami assemblies. And but there are other groups. I know that Professor Filipov here yesterday, he gave a talk. He's trying to scale things up and have actual structures then that will be susceptible to the things that you mentioned. But one thing that I may venture to say is that in front of you here, I know you are the road expert in this, but what I would like to say is this. Once we understand the mathematics, the mechanics, the behavior of these metamaterial configurations, for example, what I believe, although I have not done that, is that similar techniques that we have used for standard materials that are already there, that we have like 50, 100 years of knowledge, they could be applied. But this field is so new that there are very few people that have done that. But it's an extremely good idea and a very good point. And I hope that we will have enough time to be able to address some of those issues.
I think it's fascinating.
Yes.
Any other questions? Yes.
Professor Ching?
Nelson, beautiful talk, as always. So I remember you showed me this video last year, and when I see this again on the big screen, it's not just science and engineering, it's art. Beautiful.
Thank you.
So my question is regarding the first part of the talk. You're talking about this Lego metal materials. And notice when you press down the lowest energy, the 8 sides polygon got compressed first, right? You further compress, basically because the friction between the different cells, this 8 polygon unloaded. You rotate back, right? I agree with you that the precision is key for origami. Do you think it's possible to remove the friction between the different cells and the cell won't be screwed back? You compress 8 sides polygon, then 6 sides, and 4 sides. Is that possible? Thank you.
Very good question, Eringen. I hope it is possible. Why don't we collaborate and try to solve this problem? That would be the best.
Well, I think we're up to the time. Let's thank again Glaucio for receiving this webinar, and wish everyone have the rest of the conference and another great day.